During this session, I'm going to be talking about Newton's three laws of motion. It makes sense to start off with his first law of motion. Newton's first law of motion states, bodies will continue to move with a uniform velocity, which includes stationary, unless acted on by a resultant force. Now what this means is that, unless there's a resultant force, no object will change either speed or direction. Look at the diagram above. Although there's lots of effort involved here, all the forces cancel out, so there's no overall resultant force. So these tug-of-war teams will stay in that position until there's a dramatic change of some sort. This also explains why when you have a sudden crash, if there's no force to curtail you, so if you're not wearing a seatbelt or there's no airbag, you will carry on in the same direction you're travelling beforehand. There needs to be a force to cause change, and that includes a change in velocity. This also goes on to explain, I guess, the ideas of balance forces and static equilibrium. Why an object will maintain a static position is because if there's no forces acting on it, or no resultant force, that means all the forces acting on it have cancelled out, there'd be no motivation for this object to change position in any way. So Newton's second law of motion now could be described as the amount of acceleration that a force produces depends on the mass of the object being accelerated. This is more commonly recognised as the formula. The net force equals the mass times acceleration. So the resultant force equals the mass of the object times by the acceleration. Now this means that using this knowledge and this formula, if we know the forces acting on an object and we know the mass, we can therefore in turn also calculate the acceleration. So here's three quick examples. Take a moment to look at these diagrams and then calculate the acceleration. Now we'll go over the answers here. First of all, we have 500 newtons acting on a 1,000 kilogram car. So that means that if we work out force divided by mass is 500 divided by 1,000, which gives me an example of answer 0.5 meters per second squared. My next example shows that there is a frictional force of some sort, which is 100 newtons in one direction, and the same thrust of 500 newtons. That gives me a resultant force of 400 newtons, and therefore I can calculate the acceleration of 0.4 meters per second squared. My final situation, I could imagine a thrust of 500 newtons going forward, where this is balanced out by an air resistance and frictional force of 500 newtons. This means the resultant force is 0, so therefore acceleration is 0 as well. Newton's third law now. This is the action and reaction force. Whenever one body exerts a force on a second body, the second body exerts an equal but opposite force on the first body. So, let's think about this more closely. So if you were, let's say, applying a punch. Now the punch would have a force of A on B. Now, but we've got to remember at the same time, as this force, there's an equal opposite force, a contact force, which is going to be the force of B on A. So if you strike something or punch something, your hand will hurt as well. And this is the exact reason. So we'll have an equal and opposite similar type of force. Now, we've got to be very careful here in recognising these action-reaction pairs, or Newton's pairs, as they like to be known as. An action-reaction forces must be the same type of force. With my spaceship on planet Earth, this is the gravitational attraction force between the spaceship and Earth and space. With my man pushing the fridge, there's a contact force between the man and the fridge, and vice versa, there's a contact force between the fridge and the man. So they've got to be the same type, and they also have to be running through the same line. Okay? There can't be any two forces not running through the same central point and causing rotation. That wouldn't be an action reaction. A good example of what's not is a book resting on a table, and what we have here is we have the weight force that's acting on the book, and we also have the reaction force that's acting on the book. Now both these forces are acting on the body, on the book which we're imagining, so therefore they can't be action and reaction forces. They're also different types of forces. We have weight and we have a reaction force, so therefore these are not action-reaction pairs. So final recap. Newton's first law of motion, a body will continue to move with a uniform velocity, including being stationary, unless acted on by a resultant force. That means there's got to be a force to change speed or direction. Newton's second law, and we'll talk about momentum later on, could be described as resultant force is equal to the rate of change in momentum, but when it comes down to it, we remember Newton's law as force equals mass times acceleration. And finally, Newton's third law of motion, every force has an equal and opposite force acting on another object. Hopefully this will help you with any questions involving Newton's three laws of motion.